Okay, great. Welcome back. So now that we have like a lookup dictionaries, this kind of a lookup table. Oops, this is like a lookup table. If so, for me, I can memorize the table already, and if for you, this is too new to you, you cannot memorize everything. No worries, you can print it out and then hang it somewhere whenever you want to use any of the reparameter, right? If you want to use the reparameterization methods in the future and to look at the lookup table, and then you will see how to implement it. So if you do, if you are indeed interested in this kind of lookup table, the table per se might not be so helpful in the sense that conceptually it makes sense. So we know the parameters we want: no bound, with bound, one side bounded. And we also know how to reparameterize them. But we also would like to have a third column. If you are into this idea, you will encourage you to do so. If you are interested in, if you're into it, to prepare a third column to write down the stand codes corresponding to the reparameterization, right? Because this thing Stan doesn't accept that so much. What is the theta tutor? This doesn't, it won't be accepted by Stan. So write down in the Stan syntax how to do it. Okay, good. So now we will then be ready to go back to our hierarchical version of the Risk-Wagner model, where we have the learning rates, we have the softmax temperature. Both of the parameters, they are bounded, and we will now employ the newly encrypted reparameterization approaches to paraphrase our model. Okay, this is what we will do now. This is our original version of the simple Risk-Wagner, the hierarchical version, where we have the group level, at the same time, the individual level. So what's it will be changed is quite a lot, honestly. So originally we have individual level mu and tau. Maybe let's draw this. This is like a mu parameter group level, and then there are individuals. Okay. For the learning rates, this is the alpha. For the learning rates, the mu and the sigma, the group level, they construct this group level distribution, the normal distribution. And then this learning rate alpha will follow a normal distribution by these two parameters. Okay, this is the original idea. So if you write that down, you will have something like, I should have written it. The learning rate is followed by a normal distribution with LR mu, let's write mu like the same, and then LR sigma, okay? This is our original or the direct phrasing of the Risk-Wagner. Group level mean, group level standard deviation, and each individual, they are sampled from this group distribution, okay? What we do now is to paraphrase with the idea of Stan-Lax simple unit normal distribution. We have here unit normal, good. But also recall that this parameter, it has a range between 0 and 1. Okay, what do we do? So first, we will paraphrase, maybe I need to go back. First, we will paraphrase the part in the parenthesis, and then later, we will say this softmax part, this phi x part, the phi part, okay? The inner part has to be paraphrased, and we apply this outer function. It's like a close. You put on the close, then it becomes 0, 1. Good. So this above part, maybe we can skip. Only this part is important. So from this part to this part. So what is that? So imagine this is unit normal, okay? Unit normal will be multiplied with the standard deviation first. So the width will be changed as before, as the previous illustration. After that, we will add that to the mu parameter, it will shift the position of the distribution on the x-axis, left or right. So the inner part is paraphrased already now by this specification. After that, we will use the phi approximation. So phi approximation is a function to do this. Phi x is the S shape. So after the phi approximation with the inner reparameterized version, then each learner rate parameter will be between 0 and 1. Okay? And then there's no hard boundary or hard limit or hard cutoff. There's no arbitrary cutoff. And then for sampling, Stan will only sample unit normal distributions. So only this one will be sampled from for the algorithm, which is a unit normal. Stan lacks, everything's okay. Similar idea applies to the tau parameter, where we have the inner part, the paraphrased part, with the phi here with the phi, because for the tau parameter we want to have a parameter in between 0 and 3 or 0 and 10, which really doesn't matter. We multiply that or scale it up to the range that we want. So we will, this is pretty flexible. So this multiplication, we can multiply that with everything, 3, 5, 10, 20, everything's okay. Good. And this is the central part. And all the others, they are like roughly to help us to specify it. So here, this is the same as this line. So we want to have learner rate parameters. We want to have that many number of learner rates. If we have 10 participants, we will have 10 learner rates, and each of them, they are between 0 and 1. Only slight difference if you look at here. This is a real in the sense of the type of the variable. This is a vector. So why we are using the vector? It is because we could take advantage of vectorization to get rid of the loop. So how to get rid of a loop? Because I have a loop here. Why didn't I do vectorizing? So here we have a loop here, right? Because the slide is a little bit too old. When I was doing this, then the previous version of Stan, this function doesn't support vectorization. But if you look at the GitHub code later, I have updated that actually. So this for loop can be removed because now the newer version of Stan supports vectorization of the phi function, Yeah, good. And the ones above, you can see here, this 4 is like the learner rate, the mu of it, the learner rate, the standard deviation of it. But this is in between or within the parentheses. So that's why we have the raw part of it as well. And then this 2, what is that? So this is the individual level parameter of unit normal. So they are the unit normal. So here, these 2, they are the unit normal. So here the learning rates underscore rho, the tau underscore rho, they are essentially the same as this 2, okay? Or here. We want to use a unit normal, but to use it, instead, if you recall the idea, to use any parameter or variable, we have to declare it. We have to tell Stan how do we name it. It's like to give a name to the newly born baby. There is a baby, but we have to give a name, right? Him or her. So here, this is the name of the helping parameter, which is unit normal. Good. And with this, we then complete the reparameterized version of the hierarchical model, the Ritzler-Wagner model. So yeah, parameters block. Here we define the group level parameters. Here we define the individual level parameters. But recall in this case, both of them, they are within the parentheses. They are the X part, okay? And after that, we will apply the phi approximation so that they are lying between the preferred ranges 0, 1, 0, 3. The X per se has to be paraphrased, has to be reparameterized. Okay. If you ask me to summarize this in 2 sentences, how do we do the reparameterization in this kind of model? 2 parts. First, reparameterization of a variable using the non-centered reparameterization approach. Well, I didn't mention that this thing, so this inverse standardization, there's a name, the name is called non-centered reparameterization. First, do non-centered reparameterization. Second, depends on if there is a need to range it or to bound it or not. Depends on that, we either leave it as is or apply some other transformation functions, linking functions, so that it will be like this, in this case, 0, 1. Okay, 2. Reparameterize and apply appropriate transformation. Any questions here? Good, no? Yeah, good. And then the model part, you see that, well, originally the left one is the original direct coding, the phrase part, and then the right hand side, the other hand side, this is the paraphrased version, the reparameterized version. So what you see, this part, it will not change. So the model part, it will not change. That means, well, the Niels funnel is always the Niels funnel. We don't change the Niels funnel. So here, this is the Risk-Lavagna. This is the Risk-Lavagna. It is. We don't change the model. We just change how Stan will sample from the parameters. So originally we have this, right? Recall that we have this and this. But now we have unit normal here. So that it's easier for the sampler to sample from everything. And then the result will look much better. Good. And then this part I will explain later in the exercise part if we have the time. Well, we should have the time for that. Yeah. This now concludes the optimization of the STEM model. Any questions? Everything's clear? Or maybe overwhelming. I assume you have no questions, and let's move to the next. Okay, this is something. Yeah, okay, this is good. This is what. So we have a hypothetical data set, 10 people with the hierarchical approach. First, we could do a direct phrasing, so to describe it. And second, we paraphrase it. So first, we have a direct coding or direct modeling. The second is to optimize the model with, in particular, the reparameterization. Okay, so the left one is direct, this one is optimized or reparameterized. What you see here is quite striking. So this all of the results, they are the posterior distributions of the parameters. You see here's all of them, they just look strange. You don't like it, right? This doesn't look pleasing in a way. If visually, if I present something to you like this, and you just won't like it because it looks weird. It also basically means the result is not reliable. And if we have a result like this really doesn't look good. Okay. So the reason why this happened is because at the beginning I said the parameters, they have boundaries, they have limits lower and upper end. Normal distribution, on the other hand, it doesn't have a limit. So we want to have, we arbitrarily imposed a cutoff so that we give the range, but usually with the unlimited normal distribution, the sampler will just try to go beyond it. This causes a problem. And then this motivated our entire the last hour to introduce you the idea of reparameterization, optimization. And quite obviously, right, here to here, left to right, after the optimization, we see all of the parameter densities, posterior densities. They are the ones that we usually see. They look nice, quite smooth, and they look great. So in a way, this is the result that we could usually report to a paper. Okay. Good. This one I didn't show you, but we can skip. This is quite striking. So this is the direct coding. You see here, there is a chain which just doesn't move at all. If I remove it, if I remove the drawing, you see here, there is a line, there is a chain, which really just doesn't do much. It gets stuck, you could imagine in a way. So there are only 3 chains, they are here and here, relative to a optimized version. So all of the chains, all of the 4 chains, they mix up very well. The model, they converge to return to us a reliable results that we can draw inference afterwards. Good. And this one we can skip because later on we will repeat it. So those are like the graph summary of what we have achieved. We have the model fitting for 1 person. Here, the model fitting for multiple participants. Here we assume all of the participants, they share the same parameter. Here we say all of them, they are independent of each other. And the last one, we have the hierarchical version where we superimpose the group level distribution on top of the individuals. The direct fitting of the hierarchical version doesn't work well because of the arbitrary or the hard cutoff. That doesn't work well. So to solve this problem, we optimize our stat model or we reparameterize our stat model. What are the principles to reparameterize the parameters, or to paraphrase the parameters? We will use the unit normal distribution because this is a favorite of Stan. According to if the parameters have range or don't have ranges, then we will apply different transformation functions. This one doesn't have a transformation function. This one yes, this one yes, this one also yes. So these two, they are the softmax. These two softmax. These two, the exponential. Okay, no, exponential. Yeah. So then we have all of the tools, the weapons that we need so that we could apply all of the weapons and tools to nail all of the computational questions or models that we see in the literature. If, let's say, there's a paper that you're interested in, there is a task, there's an experiment that is quite close to yours, and they have a model, you would like to apply their model to your data, then the approach is to, as I said, code it in Stan, and with the hierarchical approach, also with the reparameterization. And then this is the trajectory you will follow when you want to have this kind of computational problems to solve. Okay. Good. This one, why there is repetition? Well, okay, good. Next question. So in reality, what I described is that you have experiment and you see the other people, they also have experiments. And this is pretty much similar. And you thought that in their paper, they also describe some model. You just wondered if you might also apply the model from theirs to your own data, right? This is pretty common. And most of the time, people will have multiple models to describe the same thing. And then they compare if one model is better than the other. So now in this illustration case, there are two models of the universe, even though both of them, they're wrong, honestly. So one model is that the Earth is the center of the universe. The other model is that the sun is the center of the universe. Both of them, they are assumptions. They are approximations of how the planet works, moves. And then you compare the model by observing next positions of the stars or the planets, and then to find out if one model is better than the other. Okay, model comparison. And model comparison has a long history, as you can see here, a few hundred years. And let's see how to do this in our case or in our scenario. So this is switch gear thing. There is no more reparameterization, not much mathematics, just the concept to see model comparison, how that works. So what is model comparison? So model comparison, essentially that means to compare models, right? So, but what do you compare? What is the criteria you will use to compare the two models? So you could imagine one thing that you will compare is the performance. So how well your model could explain the variance in your data. Okay, good. So the more the data explains your data, the better, right? You might imagine. Good. And then the second aspect is also interesting. So there is something called the model complexity. So how complex the model is. If you can explain the data with 3 parameters, and there's another one with 10 parameters. If they explain the data equally well, which one do you prefer? You might just prefer the simpler one, because if you can explain the data already with a simpler version, why do you go for the complex version? There's no need to do that. But what is the rationale of considering these two aspects? One is the model fit, so how well the model performs to quantify the data, and the model complexity. So why we care about this? Because this concerns a concept called generalizability. Okay, generalizability. So maybe we can look at this, let's go back later. So we can look at this idea. So let's say we have some data points. So all of these red dots here, so they are the data. And we want to use a polynomial regression to explain the data. Polynomial just means regression, but higher order. So we could have 0 order line, 1 order line, 2nd order line, quadratic, and 3rd order, 4th order, so on and so forth. Okay. So across all those panels, across all those plots, the data, you see the red dots, they are always the same. And now we are just fitting each dots using a different order of the regressions. So here we can say, well, there's a flat line, there is a linear line, there's a quadratic line, and so on and so forth. Okay. What you can imagine is that as long as we use even higher order polynomial regression, we can see that nearly every single data points can be fitted. Okay, so here there's a difference between the dots and the line, but here you see there's also a tiny difference, but here order 5, order 6, order 7, well, here there's also a difference, especially this two. So the line, they fit the data 100% well, okay? But is it something that you want? If all of the data points, they represent the entire population in the universe, then yes, well, maybe this is the way it is. There's no new observation, but usually this is not the case because we draw samples from the distribution with the hope that the sample will represent the distribution. So it's a subset of the sample. That could also mean we might also be able to include a new data point. So let's say we have a new data point, where it is. So let's say the new data point, let's say we decide on the best one to be here only by judging how well the model fits the data. This fits 100% well, let's say. But let's say we collect a new data point. Let's say the new data point is here. Well, you see, I don't even know where the curve goes, maybe it's somewhere down here. And then you see there's a huge discrepancy between the model and the data. So in other words, even though the 7th order regression line fits all of the previous data extremely well, there's no guarantee that this model could also provide a better explanation for new observations. In other words, it doesn't generalize. And also in other words, it has a lower generalizability, okay? So maybe let's say the new data point is here. Maybe this one is better, right? Or maybe this one also. So then there is a trade-off. The trade-off is to balance between the fit, how well the model fits the data, and the generalizability, okay? So now we can go back. So here, the x-axis is the model complexity. So the 0 order, 1st order, 2nd order, until 7th, for instance. And then the y-axis is the model fit, okay? Also the generalizability part. This is here the goodness of fit. First curve, as long as we have more parameters, the more parameters we have, the better the model fits. Easy to explain. So because there are more things, variants, that can be explained by additional parameters, good. And for this line, for this curve, generalizability. At the beginning, yes, the generalizability could also increase as the number of parameters increase. But at some point, the generalizability just reduces because it fits well, but no observation cannot be accounted for by the by the seemingly complex model, right? So here, this example, same idea. Good. And if we have a model like this, is there a word or a term to describe it? Yes. So this is called overfitting. Overfitting means there are too much parameters. Let's assume that the data contains both signal and noise. We want our model to fit the signal, but not the noise. So overfitting is essentially representing the idea that it fits both the signal and the noise. The noise part we're not interested in, so we usually do not want our model to fit also the noise. If that fits also the noise, that maybe indicates the model learns too much from the data, so overfitting. Conversely, which is less common, honestly, so it's called underfitting. In this case, well, the model doesn't even fit the signal well. Okay, it's underfitting, learn too little from the data. But this is usually practically not so much the consideration. This doesn't happen so often. Overfitting happens. But anyway, doesn't matter which one happens more or less often, they are something that we want to avoid. We do not want to have overfitting. We also do not want to have underfitting. We want to have the right balance to find out somewhere here, for instance, right? We balance well the complexity, the generalizability, and the goodness of fit, right? This is our goal. We want to find this balance. And to answer my original question, my original question is, model comparison means to compare models, but what do we compare? So what is the metric that we can use to compare the models? We use the metric of something like this. We use the balance to find out which model has the best balance. So then that one will be our target model to draw the conclusion. Okay, good. Conceptually, so far so good. And practically how to do this. Wait a sec. So practically how to do this. Practically how to do this is like there's a standard approach in machine learning quite often, or in statistics also often, which is called cross-validation, CV, cross-validation, what that means. So cross-validation means You use something to train to estimate the model and then to validate that on a holdout data set. Simpler example is like this. Suppose that we have 100 participants and we subdivide the 100 participants into 5 groups. So each of the block, each of the cell, they represent 20 participants, right? So what we do, we will use this 80 participants. We feed the model to the data, we get the parameters, and we will validate if this also holds true for the remaining 20 people. And we do this for a second time. We use this data from, again, 80 people, and then we predict the remaining 20. And then here we use this to predict that, and here we use this to predict that. And then lastly, we use this to predict this data set, okay? This is ideally how that works. As you can imagine, this takes time, right? Originally, if we want to feed the model to the data to every data point, we do all of them only once. But now I do feeding once, predicting once, and to repeat 5 times, yeah? And also depends on how large or how small we want to subdivide our data. If we divide our 100 participants into 5 groups, we do 5 this kind of thing. But if, let's say, each group only contains 10 people, we will do 10 times of this cross-validation. It takes a lot of time because we're also doing Bayesian statistics. It is already taking longer because the MCMC sampling, it is already taking a little bit longer. So it's just basically adding the complexity. If we do Bayesian parameter estimation with cross-validation, it takes some time, okay? So then people say, well, cross-validation is great. It is the ideal solution for this kind of problem. But we do not have the time, we do not have the resource. How can we get around it? Is there a workaround to approximate cross-validation? So the answer is yes. So the answer is to use information criteria to approximate cross-validation. So if you read paper from before, if you use linear mixed effect models already, or whatever models, you will see in SPSS or R, there is a matrix called the AIC, so the information criteria, the archaic information criteria. There's something else also called the DIC, the WAIC, and also the BIC. Okay, so all of these information criteria, what are they? So they are like information criteria. What are they? So they are the approximation of cross-validation. So each of them, they are like the numeric numbers for us to use to compare the models. In other words, so all of this IC, that IC is all of this information criteria. So they are representing the balance between the complexity, the generalizability, and they are trying to find out which one is the best model. So in other words, they are the criteria for model comparison, okay? So there are many of this. So this 4 of them as one example. There are many, but which one is the best? We want to know the best, and then we want to keep the best practice, right? So the best practice is this, the WAIC. So why is that? So we have, let's use the coin flipping or the globe tossing example. We have 9 times of experiments and 6 times of water, and we have a binomial distribution, and we have a theta parameter, and we feed the model to the data, we obtain a posterior distribution of the theta parameter. Okay, good. This is what we get. If we calculate the information criteria for this model, we can also do that. If we calculate information criteria for this example using the AIC or DIC or BIC, whatever we use among the 3 examples, they will only look at the top point, the peak of the posterior, which is not great. because if we have 60 over 90, if you recall, we will have a much narrower distribution, whereas it shares the same peak value if we have 6 and 9, right? But we have more data points, it becomes much more precise. There's a difference. This difference cannot be reflected by only using the peak value. It's not possible. Ideally, we want to use, maybe let's try to change another color. So ideally, you want to use every single point on the curve. Because we have the distribution, so why not using the entire distribution? So yes, use it. So the way to use it is to use here, this WAIC approach. So that's why this is much more preferred when, especially when using Bayesian statistics. Okay, so long story short, we will focus on this one for model comparison, okay? And the WAIC, according to a textbook, it is approximation, a very good approximation to leave one out. Well, leave one out is like a cross-validation. So if you want me to explain, so here, these 5 cells, you leave this cell out, use this, and then to predict this. And then here you leave this out, use this to predict, okay? Each time only leave one small set of out. Great. So the conclusion is we will use WAIC for model comparison. Next question, for practical reasons, how do we do it? How do we implement the WAIC? This is only for completeness. To calculate WAIC, there are things to do it, and you see here not so straightforward. Okay, good, we can skip. So because there is a package in R that calculates WAIC for us. But before the calculation, maybe let's look at some comparisons. Let's only look at, let's see here. So this is the AIC, the DIC, the WIC, and then this is the full cross-validation, like leave one out and then do 5 times, for example. So this is the number. This is like the AIC, this is the DIC, this is WIC, this is cross-validation. You see here, they are the same in this case. And then these two, they are a little bit different from the best solution. Best solution here, cross-validation. So conclusion is using WAIC because it is a very good approximation to the ideal cross-validation. Yeah. Good, good. So next question is, here I can skip. The next question, let's go back to the question, is how to implement model comparison. How can we calculate the WAIC? We know it's great, and then how to do it, tell me. So the WAIC calculation depends on the loop package, leave one out. So what we do is that when we do the model fitting, we will fit the model to the data, and then we can extract the likelihood from the model, and then we just simply call the WAIC function or the loop function to do something similar. And let's say we just use this one. This is too much. Yeah, good. And then the results you see here, this 58.9 is the final WAIC or the low IC score. Okay, so in the paper, this is the number that we will report for model comparison. Okay, good. Next question. If we have not only one model, we have 2 models, right? One model, you tell me, well, how to compare one model? There's no comparison. There's only one. We compared multiple models. Yeah, good. So what we do in reality is, let's say we have a fit of 1, we have LL1, and we have WAIC1. Good. We have another one, fit 2. And we do this line calculation. We have a LL for log likelihood 2, and we have a WAIC 2. Okay, do the calculation. The first one is 58.9, and then the second one is, I don't know, 40. Okay, 40. Then we have 2 numbers. Now we can compare which one is good, which one is bad. So which is which? By convention, the model who has the lowest WAIC is the best. Okay, this one in this case, because it's 40, this one is 60 approximately, this one is lower, so the second model is the best. Okay, if in reality, in some whatever examples, we have 5 models which have 120, 110, something like 180, 60 respectively, which is the best model? Well, this, right? So the lowest information criteria indicates the best balance between like the fit, between the generalizability, between the complexity. So this provides the best balance. Okay, so always look at the lowest number. This applies also to AIC. If you read other paper, if they report AIC, if they say, hey, I have 2 models, one has a lower AIC, the other one has higher, which is a good one, which is the better one. So the lower AIC corresponds to the better model. Okay, good. And if you ask me, there's a question in the chat, if you ask me what this numbers means, this is like the cross-validation scores. If you really want me to interpret, this is not interpretable. So here, this is like the cross-validation score. What that means, I don't know. It's no meaning. So they only, this on the relative scale. I know what is high, what is low. I can tell you 80 is higher than 60. So 60 is the better model. But if you ask me what 80 means, I have no idea. So it's comparison only tells you the relativity, which is better, which is worse. What really this number means is arbitrary. It's on the arbitrary scale. If you have, this also corresponds to the number of participants. If you have 10 participants, then maybe you have 80. If you have 100 participants, then maybe you have 800. This changes accordingly, right? If you want to interpret it, I really have no idea. And this is not interpretable, and nobody will ask you ever to interpret it. They will only ask you what is better, what is worse. Good. Okay, good. Next question, which is more practical, and also like Katya wrote in the chat. So let's say this is 59, okay? And I said, well, we have a model 2, and the model 2 has a information criteria score of 40. 40 is a lot lower than 59 or 60. Then it's easy decision, so we go for that. But if we have another one, let's say M3, F3, which has 39, we have 40, we have 39, which one to go for? This is quite challenging. So you will really have to judge by individual cases. Let's say if one model has 40, the other one has 39, you look at the complexity of the model. So you count the number of parameters. Maybe if this one has 3 parameters, this one has 5, well, maybe then go for that, because well, simpler is better in this case. Yeah, that's the outcomes razor in this particular example. Yeah, case by case, you have to find out the model complexity. You can't really say 39, 40, which is great. You need to go into the construction, the model per se, to find what they are, how you construct the models. Yeah. Good. Okay. So model comparison, in my opinion, is quite a large topic. We could, if we were to have the time, I guess 2 lectures can be roughly dedicated to the topic of model comparison, because there are really many things to talk about. But unfortunately, we don't have the time, so now I just only give you the gist. So So we use WAIC over all the other information criteria. Good. Or the load is also possible. So these 2 are like more or less the same. And we use that because I repeat myself, because they consider all of the samples on the posterior rather than only using the peak, right? So if you look at the literature, they will describe it in a way that it applies the full Bayesian approach to conduct model comparison rather than point estimation. Yeah, this is the kind of a standard sentence to describe it, to describe the advantage of it over the other information criteria. Yeah. So this person, this veterinary person, Aki, his name is Aki. He's a professor from Finland, and he is by far the person to go to if you have any model comparison problems. He's really active in the community. He's around, I don't know, many places. There is a question answering forum, statistics exchange, STEM forum, Twitter, some Google groups. Maybe he's active on many places. So he also provides many of his teaching materials online, YouTube and GitHub, many. And so do follow that if you're interested in the topic of model comparison. Maybe nothing related to cognitive model. He's not a cognitive scientist, not a psychologist. He's a statistician. So he has like more general overview of model comparison. If you have specific questions which cannot be answered anywhere, textbook, his videos, if nobody answers that, write to him. He replies to emails. So if you have any model comparison related questions, he's really the person, the only person to go to nowadays. Okay. Good. Something that we can relate. Let's go back to a cognitive task, moving beyond from statistics. So we have a standard two-choice task, right? In this case, we have a choice and we make a decision, we receive the feedback, and now we want to model it. Originally, we have a fixed reward rate. So imagine the 80 reward probability is associated with the blue option, and it stays there. Across the 100 trials, the blue one is always better. And what we can change the task is that we can now have a reversal learning task. So reversal means, well, in the beginning, this one is 80, and then later it becomes 20. Well, this one is 20. Okay. So first 10 trials, this is 80, this is 20, and then later this becomes 20, and then this becomes 80. And it changes back and forth a few times. So as the curve show here, well, I should have drawn 70-30, but anyways, so this is the reward probability of the yellow option. In the beginning, 70%, then drop to 30 for few trials, and then 70, 30, 70, 30, okay? So the reversal learning. The better one becomes the worst one becomes the better one. It doesn't only happen once, it happens multiple times. In this kind of experiment, what you tell the participants, you will be presented with two choice options. One is always better than the other, but the reward probability associated with the choice option changes over time. The better one can become worse, the worst one can become better. We will not tell you when that will happen. You will learn through trial and error to find out in order to gain money afterwards. So this is relatively the instruction to the participant, so that the participant know, okay, what they're supposed to do, right? They make button press and then they earn money. Good. Reversal learning. And if we want to fit the model to the data, what model can we use? Well, we can start with the simple risk-Wagner. Why not? So this is the same structure, choice outcome. As if you recall the idea, as long as it follows the choice outcome sequence, the structure, we can apply the simple risk-Wagner model under the reinforcement learning framework. Good. But there might be one alternative model, a second version of the model. So in this case, there is something in the literature called a counterfactual reinforcement learning model. So what is counterfactual? Counterfactual means to have the opposite of the fact, right? So here, if I say I choose blue, and then I receive a win, a reward. This is the factual fact. This is the factual outcome. So what is the counterfactual outcome? If you would have chosen the yellow one, what you would have received? Minus 20, right? Cents. So this is a counterfactual choice and the associated counterfactual outcome. Okay? Because we tell the participants in the instruction, we tell them one is better, one is worse. So they will then know that if they choose one, they win. They will also know if they would have chosen the other, they would have gotten a loss. Okay, this is the structure. This is the anti-correlative structure. One is good, the other one is bad, must. Okay. So now what we do, we implement this model instead. So first of all, we look at here, this line and this line, they are the same as the simple Risk-Wagner prediction error calculation and then the value updates. Good. You could also call that this is the factual prediction error and the factual value updates. Conversely, we have the counterfactual prediction error, which is the opposite outcome if you would have chosen the opposite. And then this one is used to update also the unchosen, the counterfactual value of the choice. Okay. So what you could imagine is that if you have two values in the beginning, you have a vector, right? We have a vector of two zeros. In the beginning, trial 0, and the first one is blue, the second one is yellow. Let's say you choose blue and you get a win, and you have a learning rate 0.7. Yeah. If you do the calculation according to this line, on trial t plus 1, this value will just become 0.7 and minus 0.7. Yeah, if you do the calculation. I skip that steps, but you can do it afterwards. Because if you choose 1, you get reward, then the value will increase from 0 to 1. And you also know if you would have chosen the opposite, then that's negative. So the value of the other counterfactual option will be reduced. So from 0 to negative 0.7. Okay. This is the idea. And as the procedure I described, you have now the experiment, you have the data. Let's say you have already collected the data. You have the model 2 version, simple Risk-Wagner, and the counterfactual version of it. You have 2. Now what you do is you write down the STEM model, right? You write down the STEM model in under two principles. One, we will code the hierarchical model where we have both the group level and the individual level. This is one principle. The other principle is we will optimize our model. We will already start with the optimized version. So reparameterization, vectorization, anything that we learned from today. Maybe too much, but that's the principle that we will keep in mind. Okay. So then, if we do, I skip here a little bit. So if we do the model, we write down the STEM script and we run it, and we call the Lu, the leave one out package. Now we do model comparison. So recall our today's topic is, the second part of the topic is model comparison. So what we can just we can just take a look at which model performs better. You can just already tell me the simpler Risk-Wagner or the counterfactual Risk-Wagner reinforcement learning, which one's better, which one's worse. You can guess, but there is no ground that you can guess anything from it. So we fit here this model 1, okay, model 1, and then there should have been something called model 2. I didn't write it, but anyway. So here we calculated, okay, and then this is the results. This is the results, the table. Where do we look at? If you remember, we will look at this number and this number. Great, we look at these numbers and tell me which one is better. So the information criteria scale is always 100%. The lower one indicates the better model. So these two, which is lower, this is obvious. This one is 500 something. This one is 700 something. So then we will consider the second model here, which is the counterfactual version of Risk-Wagner, the better one. Okay, this is like a simple example. But it's supposed to be real. So we have experiments, we have data, we have two models, we fit and we compare and we decide which is better and finish, write a paper. So this is it. Okay. Yeah. Good. And then there's a slightly different but also needed question, which is, well, I told you the idea that the information criteria, if you ask me to interpret, I have no idea how to interpret it. If you only give me one number, you tell me, hey, information criteria 80, tell me what that means. I have no idea. If there are two information criteria, 180, 160, tell me what is what. Okay, I can. So the 80 version is indicating the better model. Who has the lower information criteria is the better model. Good. What that means also, that implies the relativity. I can tell you which is better, which is worse. But how good that is, can I know this? I don't. So even though one is better, the other one is worse, but it's also possible that the better one is also a bullshit one. It doesn't really provide something. It's just better than the other, which is even more, it is even much worse, right? So both of them are worse. One is slightly better, but we do not want to have worse ones. We want to have good ones. So how can we tell if after model comparison, the better one is actually a good one, okay? So the challenge is model comparison tells only the relativity. We want to know if on the absolute scale, not relativity, we want to know on the absolute scale how well the model performs. This is the next procedure. So how to validate, this is like to validate the better model. If I find out there's a better one, I need to validate if the better one is also actually a good one, okay? So to validate, we use something called posterior predictive check. If you recall on the data camp, also on my previous lecture on linear regression, we touched upon the topic of posterior predictive check. That simply means to ask our model to generate choices, to generate data, and compare the generated data with the real data to see if they match, okay? So we can do that. On the x-axis, this is the trial from 1 to 100. And here on the y-axis, this is their performance to see if the participants, they indeed choose the better option. Okay, if the better option in the beginning is yellow and then blue and then yellow and then blue, we see if at this period, how often the participants, they are choosing the yellow option. Okay, just simple count or frequency. And each of the dots, so here, so they represent the data of averaged across 10 participants, for example, as a function of time, okay? Real data. And for posterior predictive check, we ask our models to generate fake data according to the parameters, and then to compare if the fake data is following the trend of the real data, okay? So one is blue, the other one is the red, pinkish color. So we see that roughly they do follow, both of them, they do follow the data, but there is a small difference. So here, this is the size of the shaded area. For the red one, the shaded area is smaller than the blue one. That means the red color is much more precise or less uncertain relative to the blue one, okay? This is not so obvious. So let's take a look at the other version of model validation. So we could also do the same calculation to count how often the participants are choosing the better option overall across all the trials, across all the participants. We can calculate the overall number of accuracy, right? Only one number. So let's say this vertical line, this is the overall accuracy. And because, you know, posterior predictive check is to ask the model to generate fake data. We could also analyze the fake data the same way as we analyze the real data. So we can analyze the fake data from this first model. We can analyze the fake data from the second model. So what you see here is that the data is like more or less in the middle of the red color. But you see here for the blue model, this is a little bit off, okay? So the red one, the counterfactual model, is providing a much more precise reflection of the real data. Okay, so this is called model validation. In summarize, that just basically means after model comparison, we find out which is better, which is worse. We asked better one to generate fake data to see if that could reflect the true pattern of the data. If that yes, then good, everything's good. And if no, you need to work on something else. Work on something else means you find out another model and you come up with a new model, fit it, compare it, validate it until you are happy with the model validation. Now you might ask me, well, how can I know if I'm happy? This is a little bit tricky. So because this is easy, only using this one as my example, I can tell you how you can be happy. So we have one true data, like here the same. If the histogram, let's say this is histogram, the center of histogram is like nearly the true data. So in this case, the red color, you can already be happy. If like the posterior predictive check gives you something like this, you are not happy. And you want to generate a new model until you achieve something like this, okay? You want to quantify that maybe. If you read a paper, how you can tell that the readers, you can say, hey, this is in the center, good. This doesn't work well. So what do you do in reality if you want to quantify that? Because this is continuous, right? This is density. If that's density, what we can do, we can calculate the area under the curve. So we know that if we draw a line here, we can calculate the area under the curve at the left-hand side of the line. We can calculate the area under the curve at the right-hand side of the line. If like this is 51, not so perfect, 51, if this is 59, 49, good. These two are like more or less the same. If this like 85 and then this is 15, no, not good. So these two has to be balanced. In this case, that's perfect. In this case, I mean, yeah. So this is the number that you can report to the audience in the paper. Okay. Are there questions so far? I'm done here. It just took longer, but I have to tell you everything so that the programming project would make sense. Are there questions? Okay, well, if not, let me give you the rough idea of the programming project, okay? Say the programming project is about nearly the same experiment. Take a choice between the two options and observe the outcome, and then make a next choice, so on and so forth. Okay, the same as before. So then there will be a data file, text file, maybe I forgot. So one column, subject ID, second column, trial ID, and then the choice, like 1, 2, let's say this is 1, this is 2, 1, 2, 1, 2, reward or punishment, win, loss, win, loss. Last column, the outcome, okay? So this is data. First thing first, write a R script. This is there, this is nearly there, and there's something you need to change. So you fix the bug. So write the R script to complete the R script so that you will read the data file into R to become a data frame, okay? Because we are dealing with data frame in R. And there are also missing trails. So in this column, the choice column, maybe some of them, they are none, okay? So because the participants at some trials, they did not give the response in time. So in this case, it becomes missing trails. What you do is that you will have to consider remove the missing trails, to remove the invalid trails, the choices. So the entire outcome of the data frame, you will, in that data frame, you will have no missing trails. So this is the pre-process of the data that we talked about many times, data cleaning, okay? Next, in the R file, you will prepare it as a data list, because stan only takes data list, and call a function called stan, right? With the data as the input and the model as another input, okay? So the actual core part of the programming project is to complete two models. We will have one, we will have two, okay? One is the simple Riesler-Wagner as before. It is already there, it is nearly there, but there are some errors or mistakes. So one of the tasks is to debug, so to correct everything in this model so that it becomes correct, okay? And the second is that we could have a variant of the Riesler-Wagner model. So to change it a little bit, so how to change it? So maybe I can use here. So we have like value is updated by value, then learning rate multiplied with PE, okay? Some people might wonder, what if the participants, they learn differently from reward versus punishment? So that literally means if the R is above 0, we will use alpha plus for the updates. And if the R, the reward, is negative, we will use something called a alpha minus to calculate, to update the value, okay? So we can call this model like a RP model for a reward punishment, okay? So what you will do is that first, debug this model so that there's no error, you can run it. Second, adapt the first model so that it has one additional parameter to incorporate this differential reward punishment effect, okay? Then when you feed the model to data, do model comparison with the loop package, okay? And as the other one, you will have the output like this. This is for the simple Riesler-Wagner, presumably, and this is for the RP, reward punishment. And then tell me which one is the better model. And then there's a file, you just tell me which is, you give me these numbers. There's a table, it's empty now, and you input these numbers, and then tell me which one's better, which one's worse. Okay, this is task. So what I would imagine or recommend you doing is, this can be challenging if you look at it. And doing that on your own might be even more challenging. So what you can do, what I recommend you do is find out another person or two. So you can have a small group of either 2 people or 3 people, and you can discuss it. And then each of you, then after discussion, you will complete the programming task individually. So I do not accept group project in the sense that 3 of you, you give me one file, I don't accept that. But you can discuss, you can have you can really have identical files, but you have to submit to me separately. Okay, so this is the rough idea for the programming project. So what is the challenging part? So the challenging part is perhaps this. So to debug in the first place, because after the debugging, you just only add one parameter for the punishment part. It's pretty easy. So the debugging is challenging, and we haven't yet talked about debugging, and this is not ideal. And what you can do is there is a recording from the last semester and on YouTube, and I can give the link afterwards in the email. So you can take a look first. And if you want to start before our next lecture, somewhere around the middle of January, if you want to do it beforehand, then watch it afterward. Otherwise, you can wait until the next lecture in January. Okay. Does that sound like a plan? Or you have no idea what to do? Okay, sounds good. Yeah. Good. When is the submission due? Yeah, good point. I have to take a look. Submission. I said it's the 7th of February, so it's 1 week after the end of January, but we can also extend if needed. February. So because the new semester starts here, right, 1st of March, and so that you will be able to select some courses for the next semester, you will need the grades somewhere here, I believe. So 7th for the deadline, I think we can do it. We can try it. If this doesn't work, we can also extend to the 14th. But that comes with the cost that you will not have to grade by this. And you might not be able to select new courses for next semester. It's a trade-off. So you decide. For me, it doesn't matter when, 7th or the 14th, doesn't matter. I will just, let's say, try to do this. Let's try to finish by the 7th, okay? Good. And is it allowed to discuss in Moodle? What do you want to discuss on Moodle? You can find out the colleagues with you, and then you can make.
No, I thought you said that we should maybe discuss it with the colleagues. I thought maybe I can, if I have a question, post it on Moodle, or it's not better to do it in groups.
No, I think you can try to find out the people you want to work with. I suggest you to organize by yourself. You find out who you want to work with. So from the breakout rooms, you might have experience with other people, and you might have some people you want to work with, maybe not. You find out. Okay.
Okay, sure.
Yeah. Good. From my side, maybe I will take a few more minutes. Okay, I briefly show you that 5 more minutes. So this is the folder on GitHub already, and then there's a subfolder called program project, right? And then everything is, the structure is more or less prepared already. And what you do is that you will double click this shortcut so that the RStudio program will be opened. And then you will see here, just a sec, it's quite slow. Yeah, good. So what you will observe is that there are multiple folders, right? So first step is to go to the scripts folder, and there you don't see much. There are only 3 files. So one is the main file, that's the learning task main, and there are 2 step models. First of all, just simply run it, right? Run it. It looks good. To load the packages and then to do preparations for you, to do initialize everything. And here at the line of 17, I already wrote a tip for you to say, well, please complete this line for reading the raw data. Okay, so where's the raw data? The raw data is in the data folder. If you follow my mouse here, the raw data is in the data folder where there is a text file. You can also open that. And then it opens. So first column, trial ID, subject ID, then trial ID, then choice, then the reward. It's the same way as I told you. So also occasionally you see the missing choice and try to find a way to process the missing trials. Okay. So then this is a line for that. Also here, write something to remove the missing trials. Good. And this part stays more or less the same. This part stays more or less the same. I forgot a lot of detail, but I think this one works. This a few parts works because I didn't even write anything to let you work on that. Good. And then later, so here I'm sure you don't need to change it because this stays the same as everything before. And there here is the place to tell R where or how do we call the models. We have 2 models, simple risk Wagner and the RP for the reward punishment. What is missing is this one here. This is the place where you need to complete something. So go back to our previous exercises to see how we call the step model. So you just basically say, well, model is what, and data is what, right? And how many iterations for 1,000, well, something like that, okay? So you complete this part. Simply copy paste from the previous exercises. And you do the same for the second model, yeah, same. And after that, so here you will need the line where I showed on the slides to extract the log likelihood. And when you have from the loop package, and when you have that, you calculate the WIC for this, the WIC for that. So this variable and this variable will look, the format will look exactly the same as this two, okay? As this and as this. And then there is this place, of course, you tell me the number, which is higher, which is worse, which is lower. Yeah. The most important thing is where is the model? So how does the model look like? The stand file. So if you remember, there's the scripts folder. Scripts folder, there are 2 models, the RP-RW, RW for Risk-Wagner. Okay, this is nearly completed. But if you remember how to check everything, so you check, there's a check button, you check it, you will see, well, there's a lot of, there is an error and there might be more errors. Then the first task of the programming project is to fix the errors, okay? To fixing that, so the suggested video from the last semester, if you want to start now or soon, you can look at. Otherwise, we can wait until the middle of January. The second model is the RP. The RP is empty. So empty means that the structure is here. We have all of the blocks, but nothing inside. What you are supposed to do is to first, as I said, debug the first model and add 1 additional parameter for differential effects of reward and punishment to learning rates. So then compare and then fit and compare. So this is the task for you. And also lastly, if you if you look at here, there's a Word document. The Word document, it has this kind of, it's like a template. It's really simple. So let's say here, this is the Risk-Wagner model. This is the second reward punishment model. I simply want you to report like these numbers, right? I only want you to report these numbers in the cell, in the table. Say if this is 400, this is what, 200. And then you tell me using a color, well, maybe something like this. You tell me, well, this is the best. You can also say, well, B, something like that. Okay, this is what you will do. So in the end, without saving. So in the end, what I need from you is like, you will change something in the script folder and you will change the Word document. And then this entire thing here, you just save it as a zip file. There's a naming guideline. So the naming is in the PDF I mentioned. Something like this. Your last name with your study matriculation number, and you give it to me. Okay. I don't need the output. I don't need the output. You don't have to give it to me because otherwise the size of the file will be quite large, maybe 100, 200 megabytes. I don't need it. And yeah, I think that's it. And then let's try to make the 7th of February deadline. So any questions here? Good, makes sense? Okay.